or sort of gymnastic sort of warm-up exercises compared to, as opposed to doing stuff related to what Christoph was talking about on the lecture today. Basically because I think he did a great job of explaining the topics, and also because it's not hard to find very interesting exercises on that stuff. We did lay out one rather crucial argument. So if you remember what Jeff did yesterday, he talked about sharp thresholds, at least in the first half of his talk. When he did, he explained that to obtain the sharp threshold for transitive monotone Boolean functions in general, you would, if you don't want to do special stuff, special calculations specific to the function you're working with, you need to apply KKL for every value of p. So you need to prove KKL outside of p equals a half. Christoph did some hints on how to do this on the lecture today. Possibly I will do the detailed proof sometime next week, but it's also possible that you'll just read it in the lecture notes, because it's the exercise or the problem session that considers these issues is really detailed, and you can ask me if you have any problems working it out. So I'll try to get us acquainted with the Fourier expansion instead. So I'll start doing the following exercise. It's called 4.2 in the lecture notes. I want to compute the Fourier Fourier coefficient of S, where f is the following Boolean function. Maps the hypercube to 0, 1. It takes it maps the string consisting of only ones, maps to 1, and otherwise it's 0. Okay, so when Christoph talked today about proving KKL and BKS, he hinted at some heuristics. One of the heuristics he mentioned was basically if you have a function whose derivative has very small support, then its Fourier expansion should be really spread out. Its energy spectrum should be really spread, if you like. And as such, this is pretty much as extreme as you get, right? This is a function which has its support in only one point, so it's really kind of sharp in that sense. So we should hopefully get some really spread out. If our intuition is correct, we should get some really spread out f hat. So what is this f hat we're supposed to compute? Well, remember that f hat of s equals the expected value of the function f as omega times ks of omega. And recall again that ks of omega is nothing but the product of the variables of the bits that are in S. All right, so how do we compute this thing? Well, f takes values 0 and 1. F takes values 0 and 1. And for the inputs that gives 0, obviously this disappears, so this is just equal to the probability that, this is totally general, nothing has to do with this particular f for the moment, probability that f is 1 times the expected value of Ks of omega, given that f of omega equals 1. This is one way to look at the Fourier coefficient. And what is this thing? Well, f is 1 if and only if the string, the input, consists of all ones. So that happens obviously with probability 1 over 2 to the power of n, right? On the other hand, if f of omega equals 1, you see how to complete from here, right? If f of omega equals 1, that means the string is just all ones. And then we really know what Ks of omega is, don't we? We just get a product over all bits in S of a bunch of ones. A product of numbers 1 is, of course, equal to 1. So this Fourier coefficient just evaluates to 1 over 2 to the n. So this was just gives you some sort of feel for how to treat these objects, how to treat these things. Was there any questions so far? Right, then I'll go to a slightly more challenging and conceptual exercise, namely exercise 3. Exercise 3 goes as follows. I'll leave you some time to think about it. If you have you consider the majority function for status. Consider the majority function. It maps from omega n to, I guess, plus minus 1. So it's always a bit dubious whether to choose plus minus 1 or 0, 1, but in this case I think plus minus 1 is a better choice. And show that the Fourier coefficients on even-sized sets disappear. Okay, so show that if cardinality of S is even, then f hat of S equals 0. So does anybody have any ideas? This sounds like a good idea, right? Because, I mean, did you carry out the calculations, or is it some intuition you've got?
Well, it's because the majority function changes sign after that swap.
Right, right. I mean, it's perfectly true. I mean, it's just the right thing to think that the majority function will change its sign if you swap every bit, and if cardinality of S is even, then also the majority will swap its sign, whereas chi sub S will retain its sign, right? Brilliant. So let's see here. I'll just write it out for the case. Write out the argument in detail for the case s equals 1 through 2k. Okay, so majority hat of s equals the expected value of, this is how I think about it when I actually write it out. I'm sure you can write it in fewer words, but if you want to see the details. This is the expected value of majority times ks. This is the sum over all outcomes. No, sorry. I don't really sum over all outcomes, or rather sum over all the outcome restricted to s. I consider what the outcome on s was. What I get then is, so this t you should think of as the bunch of guys in s that happens to have become 1 in the outcome. Okay. Well, if the guys in t were the ones that got a letter 1, well then chi sub s will be just minus 1 to the cardinality of t. Oh, sorry, t was the ones that got a letter minus 1, if I write it like this. And you get expected value of majority function conditioned on there being there are okay, xi equals minus 1 for I is in t, and xi equals 1 if I is in s minus t. And what's the probability of this happening? Well, this is, of course, 1 over 2 to the power of s, because the things we're conditioned on, are tells us what happens inside s, but doesn't tell us what happens outside s. Okay, did everybody follow that roughly? Great. And and here comes this flipping kind of argument. This is, of course, the same sum. T is in s. What happens if we flip everybody in here? So then, of course, the expected value of the majority will change, right? Because majority changes if we flip everything. Okay, so we suddenly get a minus sign over here, and oh, the crucial thing here is that now minus 1 to the size of t equals, of course, minus 1 to the size of s minus t. Which is just because s is even sized, right? Maybe you could write this out in a better way, but this is one way to think about it. Okay. But what was really crucial here in this example, as was pointed out, is that majority is a function whose value flips when you flip all the bits. When you flip all the bits, the majority function changes its value. So observe that the same argument holds. Same argument gives that f hat of s equals 0 if s has even size and f, the function f is, the function f is odd, meaning that f of omega equals minus f minus omega. Right. So this is a very natural class of functions to consider, and these all have Fourier coefficients that only live on odd size sets. Totally similarly, you could, of course, prove that if you have an even function meaning that f of omega equals f of minus omega without the minus sign over here, well, then the same flipping of everything argument would give, you would lose this minus sign over here. To get this minus sign, you should consider Here you lose the minus sign over here, so you want a minus sign somewhere else. You would get that minus sign from here if S was indeed an odd sized set. Okay. So essentially the same argument would yield that if you have an even function, then its Fourier coefficients only live on even sized sets. This should be thought of as an analogy of if you have a function, a function of real variables, for example, which you and consider its expansions in terms of cosines and sines, then odd functions will have no cosine. Odd functions will have no cosine contribution, and even functions will have no sine contribution, or the other way around. Probably the way I said it, though. Questions? Okay. I'm going to do an exercise to sort of point out the fact that these things, or rather, recall that we're not really interested, perhaps we are interested in the exact Fourier coefficients, but usually we're interested in the asymptotic shape of the Fourier spectrum, or even of the energy spectrum. We're basically interested in the total Fourier weight on level k as n goes to infinity. That's a very typical thing to be interested in. And the fact that that can be kind of hard to compute exactly, even that, we're going to do the next exercise, which is the following. Consider again the majority function, which is kind of the easiest, one of the easiest non-trivial things we've got. So we know that its Fourier coefficients on level 1 is essentially, since it's a monotone function, the Fourier coefficients on level 1 are essentially the influences. Right? Christoph told us and explained that today. And what about the Fourier coefficients on level 2? Well, they die from what we saw over there. So the next interesting case to consider is the Fourier weight on level 3. So I want you to try to find the limit as n goes to infinity of the Fourier weight on level 3, which is by definition sum over all 3-element sets of f hat, f being majority function in this case, of majority hat of s. Limit as n goes to infinity, of course. What's the first observation we will make? Sorry? It should obviously be a square here, yeah? That's the first observation we make, thank you. What's the second observation we make?
That on the 32nd page of the lecture notes, there's a formula, but it is wrong, I guess. Because this limit will not go to 0, I guess.
This limit will not go to 0, no. Does it say so on the lecture notes?
In the 32nd
32nd
page.
page.
Because on the right-hand side, there is a 2 to the m in the denominator. Probably that shouldn't be there.
Oh, that should totally be there because you multiply by m minus 1, choose m minus 1 over 2, which is of order 2 to the m. Essentially, what you say here, you have some...
But m is equal to 3 in our case, no?
m is equal... Oh, m is equal to 3 in our case, yeah? Uh-huh, okay. Okay, so there really is a formula. I mean, that's not solving an exercise to find the formula in the notes, but but okay, you claim this is faulty, you claim this is wrong. I don't know, I don't think so.
Ah, okay. Okay, then it's perfect. Okay, sorry.
But no. Oh, or maybe, I mean, yeah, this is...
No, it's okay.
I think it's okay.
Sorry.
No, there's no proof of this formula in the lecture notes, though. Is there? Okay, thanks for pointing it out. But do we have, what's the third observation we make after that I misspelled the question and that the answer is in the notes? Right. The majority function is transitive on all. It's not only transitive. It's really transitive on all the full symmetry group acts on it. So every 3 set has obviously the same relation to the function. So this is just limit as n tends to infinity of n choose 3 times majority hat of your favorite 3-element set Mine happens to be 1, 2, 3. That's what you meant? Or that's good? That's very good. So it pretty much looks like it amounts to evaluating this thing, which is, of course, the expected value of majority times x1 times x2 times x3. And here's where it gets nasty. It seems like we have to do get our hands dirty with some calculations here. Let's see what this thing is. I suppose we can condition on, we don't have to condition on the exact outcome here, but only on how many of these guys happen to be 1 in the input, right? So we get these 3 guys can together take 8 different values. And then we have to first consider the expected value of majority, given that these 3 guys all are 1. So conditioned on x1 plus x2 plus x3 being equal to 3. That has probability 1/8 of happening. With probability 3/8, exactly one of them is a -1 and the other 2 are +1s. So we get +3 times expected value of majority conditioned on x1 plus x2 plus x3 equaling 1. Plus, with probability 3/8, exactly one of them is plus. And again, with probability 1/8, we have their sum equaling -1. -3, obviously, thank you. And we can do, before we start getting our hands really dirty, we can, of course, observe that. Sorry, of course, there should not be pluses everywhere, right? Because we're taking the expected value of this times their product. So in this case, their product will be 1, so we will get a plus sign. In this case, their product will be 1 times -1, so we will get a minus sign over here. Here, their product will be 1. Here, their product will be -1. Of course. Now, essentially by the same, we can make one more observation, right? We do the same swapping, value swapping, as we did over there before. We see that if the expected value of majority sum is -1, is of course minus the expected value of majority, given that their sum is 1, right? This is just because if you flip every bit, then this event is going to transfer to that event, and majority is going to transfer to minus majority. And in the same way, of course, this term equals minus that term. So what do we get altogether? We get that this whole thing equals 1 over, so we get 2 of these minus 6 of these over 8, so we get 1 over 4 given that x1 plus x2 plus x3 equals 1, minus 3 times the expected value of majority given x1 plus x2 plus x3 equals Does this look right to you? Okay, so I won't write out, I guess I won't write out everything here, but of course, or maybe I do. In the end, so remember that majority as we defined it I might want to cheat here. So over there we defined, in the last exercise we defined majority to map into plus and minus 1. That was nice because we wanted things to cancel. This time we want to express expected values as probabilities to identify these guys. And of course we can still do that. If we map into plus and minus 1, this is going to be 2 times the probability minus 1. But it seems much nicer to let majority map into 0 and 1, right? So majority is really just the indicator function that there are more ones than zeros, more pluses than minuses, if you like. So what is this? This is a quarter times the probability that, what's the probability that there are more ones than minus ones, conditioned on the first 3 guys being all ones, the sum of the first 3 guys being 3. Well, of course, that's the probability that the sum of the n minus 3 last lads will be, I guess, greater than minus 3, right? And the probability that we will have mainly ones, if the first 3 guys are have a sum of plus 1, that's going to be the probability that the sum of the n minus 3 last guys is greater than minus 1. Well, from here, I don't think there's that much conceptually interesting things going on anymore. Do any of you? I believe you all could work this out and get the asymptotics, but I guess you all also see that it's going to take a few more lines to do it, right? If you feel like doing it, then please do, and please tell me if you get something else than 4 over 3 pi. Actually, I might double check with that expression that's in the lecture notes now, but yeah, that may be equally reliable actually as my calculations.
The second step, if we use that the majority function to change the sign when we
Exactly. Of course. Of course, so we really can't do this, right? Can we? This is Okay, so instead of expected value, we really need 2 times probability minus 1, and we need here also 2 times probability minus 1, so that's 6 times probability minus 2. Thanks for pointing that out. Okay, so as you see, I mean, there looks to be really no subtlety involved in the choice of range of this function. Then you still really have to think about which one you work with for the moment. Any questions on that?
Do you finish this with the Stirling formula? Or
Yes, I do. Right, exactly. I finished this with the Stirling formula because so essentially what happens here is, of course, that shall I do it? Okay, so I do finish it by the Stirling formula, and the observation that this probability that this thing is actually greater than. So note again a slight subtlety that we have n minus 3. We had an even number of variables here, so we can't really say that the probability that the sum is positive is a half, but we really have some extra material. Namely, we have to take care of the half the probability that the sum is exactly 0, and then we get some extra, the probability that the sum is minus 2 here, and you really have to write it out and use the Stirling formula and conclude from there. Good comment. Anything more to say in that respect? Sorry, this. You divide by the square root of n minus 3. Okay, well, if you divide by the square root of n minus 3, then you're getting normal things in the end, and yeah, I mean, you could do that equally well. I mean, sorry. Oh, right. You're concerned about that, Does this really, yeah, I guess actually, it might become less technical that way, right? Right, I mean, it's, okay, so you don't have the problem of having a point mass, but it's, essentially you obviously you hide the problem into finding the or into the very well established work of the finding the distribution function of the normal distribution. But yeah, I agree that it might be preferable to divide by square root of n minus 3, but I don't think that's. I mean, the main point of the exercise so far is just to show that these things are kind of elaborate to compute in general. I'm going to hint at you, if I have time, and I hopefully do, in the end, another way to find the spectrum of this particular function, the majority function, which also really, I mean, to an extent, does the same thing, but in a more uniform way, using generating functions. But that one also really relies on the fact that and that's what's crucial here, that the majority function can be, that we can do calculations with it, that we can do Gaussian calculations with it. Whether we explicitly go to normal distribution or not, then it's really the rather unusual fact that majority function can be calculated that helps us. Yeah. So I'm going to show some of what the Fourier coefficients and the Fourier expansion is good for. Again, though we've seen it a few times. For that purpose, I'm going to the exercise 9, what we call exercise 9. So we define something we call the stability function. The stability function is defined as it takes epsilon and maps it to the probability that f of omega differs from the noised version, f at the noised version of omega. So recall that. Okay, so how should we understand this? Obviously, the more we should think that the more stable a function is, the smaller this probability should get, right? So the smaller the function, the stability function should get. This is also exactly the function, if we recall the definition, exactly the function that we want to go to 0 with epsilon. Well, every function for every f, this goes to 0 with epsilon. But we want it to go to 0 uniformly in n. If it does, then we say that Fn is a noise stable sequence. Okay, so what about it? Can we perhaps express this function in terms of the spectrum? Yes, we can, and it's not too horribly hard. I'll ask you how to do it once I've erased the board. So now I've erased the board, so you tell me how to express this in terms of how to start if we want to express this function in terms of the Fourier expansion of f. Ideas? If I'm thinking Fourier expansion, I'm thinking a lot of things, but one of the things I might think is linearity. If I want to expand something linearly, it's nicer to look at expected values rather than probabilities, obviously. So we can write this as, to start with, Suppose we're mapping in 0 and 1, and we're writing this as a quarter of expected value of f of omega minus f of omega epsilon squared. Does that make sense to you? So the probability that f differs in these 2 points is, of course, just the difference of the values squared. Using that, f only takes the values plus and minus 1. And you have to divide by 4 of that. From here, it largely amounts to counting, calculating. So what do we get? We expand this, we get 2 times the expected value of f squared, right? F of omega squared, f of omega epsilon squared, but they don't both have the same expected value. Minus 2 times expected value of f omega times f omega epsilon. F maps into plus minus 1, so f squared is constant 1, so its expected value is also constant 1. So here's just half 1 minus the expected value of the product here. This might be a good place to start Fourier expanding, I think. What do you think? So I'll Fourier expand each of these lads. And I'll get the sum over, double sum over S and T, f hat of S, f hat of T, chi s of omega, chi sub t of omega epsilon, end of that parentheses, end of that parentheses. And now we observe the same thing we've observed a few times before, that whenever S and T are not equal, whenever these sets are not equal, then this is going to be the product of a bunch of S. Whenever if there's something in T that's not in S, then we certainly have no clue whatsoever what this character might be, since they're orthogonal. So the terms where S and T differ will cancel, or rather the expected values will be 0, and we will get a half times 1 minus the expected value. Maybe we bring the sum outside. Sum of S, f hat of S squared. Expected value of f of omega epsilon. Yes, of course. Here's supposed to stand chi s. So recall that we cancelled all the terms where S and T differed, so we just have the same S here and here. Okay. So where do we go from here? Well, again, we observe a thing we've observed a few times before. look at this in many different ways, but we think about this as, okay, omega epsilon is the version of omega where we re-randomized every bit with probability epsilon. And if we've started to re-randomize something in S, then certainly we can't know anything about it, and these things will be independent of each other. So the only way we can have something non-zero here is if omega epsilon really didn't change from omega on the bits in S. And what's the probability that happens? That happens, of course, with probability 1 minus epsilon for each of the bits, so 1 minus epsilon to the size of S. We've seen it before, but I'm repeating the argument because we're going to see it so many more times. So in the end, we're getting a half minus a half times the sum over S f hat of S 1 minus epsilon to the size of S. And I guess this thing will be the same on, this only depends on the size of S, so we can rewrite this in terms of the energy spectrum just so we can use that. Once we've defined it, we might as well exploit it. Half sum over K, the energy of F at level K, 1 minus epsilon to the power of K. And there we go. So there you have the stability function expressed in terms of the energy spectrum. Questions? So from here, it's a good starting point to enter the totally marvelous exercise or problem number 911. Oh, what a beautiful name of an exercise, by the way. It's a rather nice one, really. It's a very cute way of calculating the limit of the spectral distribution for the majority function as n goes to infinity. So we want to understand the asymptotic shape of the spectral. We want to understand the asymptotic shape, really, of the energy spectrum of majority function of n. So what do we mean by the asymptotic shape of this? We want to understand the asymptotics of this thing as n goes to infinity. So we want to understand i.e. we want to calculate the limit as n goes to infinity of energy spectrum of the majority function on n bits at level k. Want to calculate this thing for every k. That would make us very happy. So we already did it for k odd, obviously. For k even, obviously. because we saw that for even-sized sets, the Fourier coefficients of an odd function, such as the majority function, will disappear. We essentially did it for k equals 1, because there because majority is monotone, so the Fourier coefficients on level 1 is just the influences. Right. So we also did it, or close to did it, at level 3, k equals 3, by doing some actual hands-on calculations. That wasn't so fun, but it at least was possible to do. But doing it for all k simultaneously, how would we go about doing that? Well, the first step would be to see that, to somehow exploit the stability function. The stability function is something we can understand, right? This is the probability that the function differs in two different values. This is rather understandable. This in turn gives us a power series expansion. This has a power series expansion, which is essentially just the very closely related to the energy spectrum. Okay, so if we could calculate this function over here, the stability function for the majority function, and power series expand that stability function, then it would be a good way. Would have a fair chance of understanding the energy spectrum, or we would understand the energy spectrum because the coefficients would just be the same. So the first step, I'm not going to go through this whole problem session because it has a bit too many calculations, but I want to hint on how to do it. So first step, would anybody, so I've already hinted that we should look at the stability function. Would anybody tell me how to do that, to go about doing that? What is S sub majority sub n of epsilon?
I think you'll have to use the central limit theorem, but the two-dimensionals.
Yes, that's very true. That's quite true. So observe that we're interested in limits as n goes to infinity, right? For every epsilon. So note that these things basically f of omega is different from f of omega epsilon. That just means that the sum of the variables in their original version is takes the sum of those take a different value than the sum in their noised version. So the probability of this happening is 2 times the probability that the original sum was positive, whereas if we flipped it, if we re-randomize the fraction of them, it becomes negative. Okay. But xi, okay, so note that xi epsilon, we don't need to view one of them as a noised version of the other. We can look at them as 2 identically distributed but not independent variables. These are both Bernoulli a half. Well, they are 1 with probability a half, they're -1 with probability a half, and they have they have covariance 1 minus epsilon, right? Okay. If we sum this, then these things, this guy here and this guy here, are going to be asymptotically, they're going to be normal 0, 1s with correlation with covariance n times 1 minus epsilon. Sorry. We should obviously normalize them, so divide by square root of n. So this is, as you pointed out, this is by central limit theorem in the two-dimensional case. We get something like this, right? This is this thing becomes 2 times the probability that a standard normal z is positive, whereas its body z prime is negative, where z and z prime are centered normals, centered jointly normals. Distributions with covariance, what's their covariance? I've normalized, so they each have variance 1 and they have covariance 1 minus epsilon. All right. So we were interested in this. We were interested in this limiting shape, and then this squiggle is going to give us the right thing. So now we just calculate this probability in the limit. Calculate this probability in the limit, and we get a nice. We just write down the two-dimensional Gaussian integral. We calculate it. We get different things each time we calculate it. Suddenly we get the same result twice, and we decide that that's the right one, and that's something involving Arcus cosine. Okay? Doesn't really matter what it is. I mean, obviously it matters, but not for the idea. So you get the limit of this thing, SF of epsilon. You get this as a function of epsilon that you get explicitly. You power series expand that guy, and then you would hopefully get the same power series expansion as this thing here. To be sure that that happens, you need to check that the convergence, that everything behaves nice around the point at which you power series expand and around epsilon. That's the second part of the exercise, and once you've done that, you're pretty much ready to calculate the limit as n goes to infinity of this energy spectrum. It's rather complicated. I mean, it has a few steps and rather many calculations, but it's really a nice exercise on how to get this and how to exploit the generating function in this situation. On the other hand, it's kind of unsatisfactory from a Fourier analytic point of view, perhaps, because it's really specific to the majority function. It's really crucial that we're working with a function with which we can do explicit calculations, I mean, Gaussian calculations. So I recommend you to do that over the weekend because we don't have a lecture for 2 days. And feel free to come and discuss with me when you've done it. Is there something else I want to say? Yeah. I started a bit late. I would like to do exercise 4.10 as well, if that's all right with you. So I'm curious, among all balanced Boolean functions, which is the stablest one? Is there any balanced Boolean function that's stable, more stable than everyone else? What would being most, what does balanced mean? Balanced means that the average, that the mean is 0. What does most stable mean? Most stable means that the stability function is as small as it gets. Why do I need the balanced assumption? Well, if I don't have it, then I can think of one extremely stable function, namely the constant one. I can think of two very stable functions, namely the two constant functions. And if I ignore these, then I can think of other very stable functions, for example, these that only take the same value in every point but one, for example. So I'm really curious about among balanced functions. So using only things that I've left unerased on the board. Does anybody have an idea? So is there any function f star from omega n to plus minus 1 which has mean 0 and the stability function of f star is smaller than the stability function of any other f at every epsilon. Suggestions? So we had one. We had one from the front, said majority function. Is an idea? Right, right. So it's. So that's a very stable. So we've seen that we've seen some evidence that majority is very stable, and there are indeed theorems that say majority is stablest and such things. But that's usually among functions with some certain symmetry considerations and symmetry restrictions. For example, I showed yesterday that. It really has the highest total influence among transitive functions. You had another suggestion down there? I'm sorry, I can't hear you. Functions there. That's an idea. I really would like to look at this thing here. What does it mean? F star. We're only looking at balanced functions. We're only looking at balanced Boolean functions. That means that exactly that expected value of f is 0. Expected value of f is just f hat of empty set. This cannot be said too many times. So f hat of empty set equals 0. So can we, in some way, we want to in some way bound the stability function of balanced functions from below. We want to bound this thing from below. Obviously, it should be not strict inequality there. Well, this is we've got an explicit expression for the stability function over here, and if well, maybe we look at this line instead. And if we only look at balanced functions, then we have f hat of s disappearing. F hat of s disappearing means that this, all of these things are, oh, there should be a squared there, obviously. So, right. So that's not going to be anything, and now this thing is, so everything is going to be greater than or equal to 1/2 minus the sum of sum over all sets S of f hat of S times 1 minus epsilon. Because 1 minus epsilon to the power of the size of S is going to be, size of S is going to be positive, so it's going to be at least 1 here. Square over here. And, yeah. 1/2 is, sorry? Where?
Second term.
Oh, second term, of course, yes. Now, recall that a function that maps into plus minus 1 is always going to have second moment equal to 1. Second moment equal to 1. Now, summing over all s's f hat of s squared, that's just taking its second moment, because this is an orthogonal basis. This is the possible identity, or if you like to call it the Pythagorean theorem. So this thing I've just written down here is 1/2 minus 1/2 1 minus epsilon, which is indeed a function that doesn't depend on f at all. It doesn't depend on f at all. So this is, so I have indeed bounded this stability function in terms of epsilon. Now I'm only curious, is this ever tight? I bounded it. I wonder is this ever tight? Well, is it? Oh, yes, it is. Because if all the spectral mass actually was on level 1, if all the spectral mass was on level 1, then 1 minus epsilon to the size of S is indeed equal to 1 minus epsilon. Okay. Equality, if all the spectral mass is on level 1, what does that mean? That means our function is sum over all s's. It really has all its, it really can be expressed in terms of only the sum over all k, sorry, over as the in terms of the chi-s's for one element sets S. So it should be written as some constant times the k's, k sub element k. Well, what's chi sub k? That's just the product of the bits in k. That is just the bit xk. So equality holds exactly if f is indeed a combination, a linear combination of the variables. Now, if a Boolean function taking values plus and minus 1 is a linear combination of its variables, well, then it must, of course, be one of the variables, because as soon as you start adding more than one of them up, then you're going to get either too big or too small or two non-integer numbers. So f is indeed plus or minus xi for some I. So what have I just proven is that the dictatorships, meaning the functions that are determined by one bit alone, are the stablest ones. That's all. If you have any questions, please ask me afterwards. Let's go for dinner.